Hello, welcome back. So we are looking into some of the numericals of damped pre-vibration. So in the previous presentation we have seen two different numericals, and now we will see the third numerical. So in this numerical it is specified that an underdamped shock absorber is to be designed for an automobile. It means definitely it will be having this kind of fluctuations since it is under damped one. Okay, so it is required that the initial amplitude to be reduced to 1/16th in one cycle, and it is expected that whatever may be the amplitude in the first cycle, it should reduce to 1/16th in the second cycle itself. So much reduction in the amplitude is expected here. So the mass of automobile is given as 200 kg, and the damped period of vibration is 1 second. So time period of vibration is given here, that is 1 second, and you are asked to find the necessary stiffness and damping constant of the shock absorber. So since we are designing the shock absorber, the shock absorber is having generally provided with a damper and a spring. So you have to find out the stiffness of that spring, and you have to find out the damping coefficient of that absorber. What is expected here, that x1 by x2, this ratio should be equal to 16. Okay, and this is mass and time period is given to us. Now let us see that the available decrement which is required here, x1 by x2 is 16. So we call it as a logarithmic decrement, which is given by delta is equal to 1 by n log to the base e of x0 by xn, where in this expression this en is nothing but the number of cycles. So as in this given problem the number of cycle is only 1, so delta will be equal to 1 by 1 log to the base e of 16, since x1 by x2 ratio is 16. So we will get the delta is equal to 2.7725. Also we know that this delta is given by 2 pi zeta upon in under root 1 minus zeta square. Therefore using this expression, now only there is one term, that is zeta here, which is unknown. So this zeta can be determined. Okay, and this zeta is equal to 0.4037. okay, that is nothing but the damping factor. So also we know that the time period is nothing but given by 2 pi by omega d, and therefore omega d into time period will be equal to 2 pi, and that is equal to under root of 1 minus zeta square into omega n. So using this expression, now we will determine the value of omega n, which is equal to 2 pi upon in under root 1 minus zeta square, which is nothing but equal to 6.86 Radian per second. Since you have got the omega n, once we get the omega n, this omega n is equal to under root of k by m, and therefore k is equal to 9423.45 Newton per meter. So this is the way that you have got the stiffness by using this particular expression of time period. And okay, so here you see time period was given 2 pi by omega d, and we are putting the value of omega d into Tp will be equal to 2 pi. Okay, and omega d is nothing but equal to under root of 1 minus zeta square. So 2 pi upon under root of 1 minus zeta square, that is omega, and that you have obtained here for this expression. Okay, so once you got omega n, that you got the value of k also, since mass was known to you. Now we have to find out the damping value c. So we know that zeta is equal to c by cc. So cc is nothing but equal to 2 m omega n. So we are already having this m and omega n with us. So if I put those values, so I will get the c is equal to zeta into 2 m omega n, and that gives me the value as 1017.75 Newton second per meter. So this is the way you have got the value of the damping coefficient and the stiffness of the shock absorber, which is required to be designed. Okay, so in the next example, now we will see here that there is a machine of 75 kg mass. So mass of the machine is given as 75 kg here. Okay, and it is mounted on 3 springs. So there are 3 springs, okay, on which it is mounted. So each of stiffness 10 Newton per mm. So stiffness of this 3 spring is provided, which is equal, and it is fitted with a dashpot to damp out the vibration. So it is also provided with a dashpot. Okay, and during vibration it is found that the amplitude of vibration diminishes from 40 mm to 6 mm in 2 complete cycles. So what they have observed, that the amplitude of vibration will decrease from 40 to 6 mm in 2 cycles. So you have to determine the resistance of the dashpot at unit velocity c. So you have to find out this dashpot resistance. Then frequency ratio of damped vibrations to undamped vibrations. That means omega d by omega. This ratio you have to find out. And the time period of damped vibration, that means TP, you have to find out. So let us write down the given data first. Mass and stiffness is available, and the x0 and x2 is available, means after 2 cycles. Okay, so we can get the logarithmic decrement here. Now first we'll combine these 3 springs to get the equivalent stiffness. So it is in parallel, so k1 plus k2 plus k3, that is equal to 10 plus 10 plus 10 equal to 30 into 10 to the 3 Newton per meter. Okay, so once we get the k equivalent, we can find out the natural frequency of the system. Omega is equal to under root of k by m, because m is 75 kg. So if I put this value of k and m here, I will get the omega n as 20 radian per second. Now with this, now I will try to find out the logarithmic decrement. So delta is equal to 1 by n log to the base e of x0 by xn. So 1 by 2, since 2 cycles are there, log of 40 by 6. So you will get this value as 0.9485. And also we know that this delta is given by 2 pi zeta upon under root 1 minus zeta square. So using this expression, I can find out the value of this zeta. Or another way there to calculate the zeta is delta upon in under root of 4 pi square plus delta. By using this expression also we can find out the value of this zeta. So if I put the value of delta here, 0.9485 in the numerator, and in the denominator 4 pi square plus this again delta value. So I will get this value of zeta as 0.1491. Now this value of zeta I will use to find out the value of c. So since zeta is 0.1492, so c by cc is nothing but the zeta, and therefore the c becomes this zeta multiplied by 2 m omega n, which gives out to be 447.80 Newton second per meter. Now the ratio of damped vibration to undamped vibration, that means omega d by omega d, omega I have to find out. So I know that omega d is given by omega n under root of 1 minus zeta square. Okay, and I have already got this value of omega d here. So the ratio of omega d by omega becomes 0.9888, and the time period of damped vibration, so TP is equal to 2 pi by omega d. So 2 pi by omega d is again writing this value of 19.77. I will get this time period as 0.3178 seconds. Okay, so also we will see one more numerical. Now in this case it is given that there are 2 slabs of isolators, natural rubber and felt, okay, which are kept between a solid mass of 10 kg and the floor as shown in figure. So there is a floor at the bottom, here there is a one mass of 10 kg, and natural rubber and felt, these two materials are kept over each other. Okay, and neglecting the mass of the isolator, determine the and undamped natural frequency of this particular system. So here you will find out that the stiffness and damping of the natural rubber is given, and for the felt it is given, which is 1200 Newton per meter and 330 Newton second per meter. Okay, it means this system we can show it like this, that mass is there and below this there is one stiffness, natural rubber stiffness and felt stiffness, which are in series, and also this there are 2 dampings in series. Okay, so now let us try to find out this equivalent value of the stiffness and equivalent value of the damping. So equivalent stiffness is 1 by k is equal to 1 by k n plus 1 by kf is equal to 2400 Newton per meter, and similarly the equivalent stiffness is 76.74 Newton second per meter. Once we get that, we can find out the natural frequency, which is given by under root of ke by m. So if I put these values of k as 2400 and m as 10, I can get the 15.49 radian per second as the value of omega n, and therefore the omega d becomes omega n into in under root 1 minus zeta square, nothing but the damped natural frequency, and this is nothing but the damped natural frequency. So again, if I write it here, To find out this omega d, I need this value of zeta. So zeta is equal to c by cc, that is cc upon c upon 2m omega n. So equivalent stiffness I have written here, and 2 into m into omega n. This value is 0.247. So if I use this value of zeta here, I will get that omega d as 15 radian per second. And in terms of hertz, it will be 1 upon 2 pi into omega d. So 15 upon 2 pi, that will be equal to 2.38 hertz. So this is the way we can get its natural frequency, damped and undamped condition. Now we will see one more numerical on top of the torsional pendulum. So a disc of torsional pendulum has a mass moment of inertia of 0.06 kg per meter square, that is given to us, and a brass shaft attached to it is of 100 mm diameter, and 400 mm is the length of that particular shaft. Okay, it means a shaft is there and a disc is there like this. Okay, for having this particular torsional vibration. So length of this shaft is given, diameter of this shaft is given, and mass moment of inertia of this particular disc is given. So when pendulum is vibrating, observe amplitudes on the same side of the rest position for successive cycle is 9 degree, 6 degree and 4 degree. That means whatever the amplitude of vibration is there, means the theta is there. So initial amplitude, then the next amplitude, and the third amplitude, it is goes on decreasing. So suppose it is given in terms of degrees here. So initially it is 9 degree, okay, then it becomes 6 degree, and then it becomes 4 degree. Like this is the reduction. Okay, and you have to find out the logarithmic decrement. Second, you have to find out the damping torque at unit velocity and periodic time of vibration, assuming modulus of elasticity as 4.4 into 10 raised to 10 Newton per meter square. So let us see how we can do this. At the same time, it has been asked to what would be the frequency if the disc is removed from the viscous fluid. So in the undamped condition, what would be the frequency of it? That is also asked to find out. So I am specifying the for this particular disc I as 0.06, diameter of that shaft and length of that shaft. Theta 1 is 9 degree, theta 2 and theta 3 is 4 degree, like this. So first I will find out, right, you can write it in terms of theta or in terms of x, there is no problem. So if I write here x0 by x1 is equal to 9 by 6, that is 3 by 2, and x1 by x2 is equal to 6 by 4, that is equal to 3 by 2. It means I can say delta is equal to 1 by n log to the base e of x1 by x2, so that is equal to 3 by 2 is the ratio, means for one cycle. So delta is equal to 0.405. So once we get the delta, okay, logarithm decrement, so we can determine the zeta by using this. So delta upon in under root 4 pi square, okay, plus delta square. So this way you will get the value of zeta, which is equal to 0.0642. And now I have to determine the torsional stiffness Kt, which is given by G into J by L for that particular shaft. So G value is specified, J value is pi by 32 d raised to 4, and L is 0.4. Okay, so this I am getting as 1.08 into 10 to 6 Newton meter per radian, and omega n is equal to under root of Kt by I. So Kt I have got torsional stiffness, and mass moment of inertia is I is 0.06. So I will get this 4242.64 radian per second as the omega n. And as the value of zeta is c by cc, so in this case it is ct upon I into omega n. So from here I will get the value of ct also, which is equal to zeta multiplied by 2 multiplied by I multiplied by omega n. And if I put the values of all this, I will get this ct as 32.73 Newton meter per second per radian. Now the time period of damped vibration. So for that I have to determine the omega d first. So omega d is equal to omega n under root 1 minus zeta square, which is equal to 4233.86 radian per second. And to get the time period, I will write this 2 pi by omega d. So I am getting this time period as 0.00148 seconds. So the frequency if the disc is removed from the viscous fluid, so it will be nothing but omega n, because it is without damping. So Fn is equal to omega n upon 2 pi, so it is 675.74 hertz. This is what is the solution of this particular numerical. So here we are going to stop. Thank you very much for watching.